Okay, what do we want to do first with this question?
Like convert Fahrenheit to Kelvin.
Yeah, I go Kelvin, Fahrenheit to Celsius and then to Kelvin because I've got Kelvin units in my entropy, and so I won't be able to cancel it out otherwise. So it's 62 minus 32 times 5 ninths. Let's see if that's right. Times 5 divided by 9 equals. Yeah. So that's 9, say 9.3. Okay. And then 273. So 282.3. Okay. And then what's the other thing we need to do?
Kilojoules.
Yeah. I convert this to negative 2200 joules per mole. And so then delta G will be equal to negative 2200 joules per mole minus 282.3 K times 9 joules per mole. Okay. The K's cancel. Times 9 equals plus negative 2200. I got negative 4740 joules per mole. Okay. So what's the answer to this?
Yes.
Could you have answered it before doing any of the math?
Someone could have. I could answer before finding the final answer.
I'm hoping that you would have been able to answer this before doing any of the actual math for it, though. How's that?
That's the change in H is negative.
Yeah, because
And the change in X is
energy,
not.
it lost energy and it gained disorder. So it doesn't matter what the Fahrenheit temperature thing is, you could just say it's spontaneous, because it's, entropy went up and enthalpy went down. But now we have a number associated with it. All right, we're gonna draw and label a voltaic cell of zinc and magnesium. Calculate the voltage. Okay. So, put a beaker here and a beaker here. The salt bridge thing is really just like it's like a test tube that's open on both ends. That's in the shape of a U. And you put you've got you're holding it like this, and you fill it up with salt water, and then you stuff some cotton balls into both sides, and then you just flip it over and put it into the beakers. So the cotton ball mouths are both open, or both in the water. That's how it works. So level here and a level here. So inside of here, I don't know, I'll just put potassium nitrate, just for the heck of it. And we have zinc, so I'll put a zinc bar here. And I'll put a magnesium bar here. And I'll have them attached with a wire. Put a voltmeter in the middle just so we can measure the voltage. And what needs to go into the liquids? No, not just that. That's what'll happen when the battery starts to discharge. So one of these metals is going to be giving electrons away, right? So where are the electrons going to go? Right now, there's no place for them to go. Because for something to give away electrons, what has to happen?
Something
Something has to accept it. So first, which one of these is higher on the list, the magnesium or the zinc? Okay, so that means the magnesium will be giving electrons to zinc. Great. Okay, so when these magnesium atoms on this bar start sending electrons over, and they're going to be sending 2 electrons over each time. Why?
Somebody has to do it.
Yeah, magnesium's a group 2 metal, so its options are it has all of its electrons or it's lost 2 of them. There aren't any other possibilities. So one of the magnesiums on this bar gives away 2 of its electrons and then goes into the solution and becomes magnesium plus 2 aqueous. Great. So those 2 electrons went over to that other beaker. Is there any place for them to go? So far, with what we have drawn so far. Nothing over there is going to accept it, right? There's a zinc metal, and zinc can't become negative, so what are we missing from this?
You have to add something on. It's positive charge.
In the solution. Already has to be there. So in the solution, you have to have some metal that's already been oxidized. And so now the magnesium can send its electrons over. And when these electrons get here, what happens?
And they turn back into solid.
Then this zinc that's already in the solution grabs hold of those 2 electrons and becomes zinc metal and just sticks to the bar. So to have a battery operate, you need to have a metal that's willing to give its electrons to another metal, right? But the metal that it's giving its electrons to, what has to be its current condition?
An ion.
It has to be an ion. Absolutely. It has to be an ion. It has to be willing, you have to have something that has the ability to accept electrons. And a metal that's an element, like the zinc bar, is not able to accept any electrons. So in the solution, I'm going to have some sort of metal ion. So why did I choose zinc nitrate? Nitrate is soluble. You wouldn't choose, I wouldn't try to dump like zinc oxide in there because zinc oxide is insoluble. It would need to be an element whose anion would let go of the metal. So I always invariably choose nitrate. Why? Because it's always soluble. It doesn't matter what the anion is, or the metal is that's attached to it, is going to let go the second it hits water. Okay.
So is there also K pluses floating around in there? No?
So now that this electron has gone over, those 2 electrons have gone over to the other side, what just happened to the charge in the beaker on the left?
Or negative.
It became -2 charge, right? So that has to be negated or neutralized or canceled out. So what do you need to put into the beaker? 2 potassium pluses. So here, 2 of these potassiums are going to have to go into this beaker. So also on the other side, a magnesium just went, with a +2 charge, just went into the beaker because 2 electrons left. So what now needs to go into the beaker?
2 nitrates.
2 nitrates. These guys need to go down here. And that's the purpose of the salt bridge, to make sure that the beakers have a charge equal to 0. All right. I didn't ask for it, but what's this shorthand cell notation for this? What do we start off with?
Mg is a solid.
I had this magnesium metal, and this magnesium metal turns into magnesium ion that's aqueous. And then what happened?
Are you on your face?
Had my what?
Zinc metal.
Zinc metal?
Zinc.
The zinc that was not a metal accepted those 2 electrons and turned into zinc that is a metal. So the thing on the right, the shorthand notation, is enough information for you to draw the diagram on the left-hand side. What's the voltage that's going to be created with this? So let me open up the notes.
So in your picture, the anode was on the right.
Yeah, sure. The anode was on the right. Yep. Yeah, that's where the electrons came from. But in the cell notation, the anode will always be written on the left. Notes. So what we had was magnesium losing electrons. Do we have that here? We have magnesium gaining electrons. So if magnesium, a magnesium atom, were to gain 2 electrons, how does that work? How do you get that to happen based off of this?
You had to add that much energy.
I gotta put 2.38 volts of electricity into that process to get that to happen. But since the magnesium was actually giving the electrons away, I get that much voltage. So 2.38 volts, that was generated. And then we have to check the zinc now. So the zinc's a little bit further below, and this is drawn correctly, right? I have zinc ion gaining 2 electrons, turning back into zinc metal. And to do that, it also takes electricity. It takes 0.76 volts of inputted electricity. So the voltage that we generated, the 2.38 volts, some of that's going to disappear. So I'm going to add negative 0.76 volts to this to get myself an overall voltage of 1.62 volts. Is this a good battery? Yep.
It's about 1.2, is that what you said?
No, 1.5.
Oh,
So it's above 1.5. This is the high end of what like a AA or AAA or C or D battery would be generating, brand new, and these metals aren't that expensive. We talked about that Gasner battery last time, and it's got a zinc casing, so zinc is definitely one of the 2 things. What was the other piece that was accepting the electrons? It wasn't actually magnesium. So you remember what it was? Yeah, it was a piece of carbon. So it's actually cheaper to have the thing that accepts the electrons be graphite than it is to be zinc metal. Does that make sense? Or sorry, magnesium metal. Magnesium metal is more expensive than a piece of charcoal. That's basically what we're saying. Okay, so which metal is being reduced and which is oxidized? So who's being reduced? The zinc is definitely being reduced, right? Its charge went from +2 to 0. And so that means that the metal that's being oxidized is the magnesium, because it went from 0 to +2. And these other 2 terms. So what's the reducing agent? The magnesium. It's the thing that's doing the reducing. So the magnesium is the thing that gave the electrons to the zinc to allow it to be reduced. So the magnesium is my reducing agent, and my zinc is my oxidizing agent. Because what did the zinc do to the magnesium? It oxidized it.
Would it be the zinc ion or the zinc?
Just zinc. It would definitely be the zinc. The zinc ion is the oxidizing agent for sure, but you just need to say zinc, because the zinc metal obviously can't be an oxidizing agent. Where have you heard that term used before? Oxidizing agent. Cleaners, absolutely. So bleach is an oxidizing agent. So what must oxidizing something do in terms of clothing?
Take stuff off of it? Like takes the dirt off?
It allows the,
Not that.
it allows like the actual like to clean? I don't know.
No.
Supposed to give away their dirt?
Nope, but that's a good second guess there. No. What happens when something becomes oxidized in general is it loses color. So I've got a substance, it's on my white t-shirt, it's pink. And this substance, when it becomes oxidized, it's losing its electrons. And normally when colored things lose their electrons, the color disappears. But what didn't it do?
Actually get rid of it.
It didn't actually get rid of it. You might have been in a situation where you were wearing a shirt that you know is clean, and then you find yourself standing next to a black light looking at your shirt going, this thing is filthy. Has that happened before? I had like this favorite white t-shirt that I wore for like 2 years, and then I'm standing at this black light at this, they used it to like check to make sure that you could get back into the concert okay. Like they were checking like your wrists, and then as I got close to it, it just looked like my shirt was camo. There was so much stuff on it, but outside of the black light, it looked completely white because I would bleach it. So there are definitely still stains on the shirt. It's just that you can't see them. So when you're oxidizing something, when you're using like a bleach, or you're using like a hydrogen peroxide or OxyClean, which is basically in situ hydrogen peroxide, what's happening is the stain that's on the clothing is losing its color, but not going away. Will electrons be transferred if you react magnesium, metal, and mercury ions? So I've got magnesium, solid, and I've got some mercury, let's say mercury 2, aqueous. Is anything going to happen here? Something will happen. The electrons from the magnesium will be transferred to the mercury. How do we know that?
Because mercury, or not mercury, but magnesium has 2 electrons to give away.
Okay, so this guy has electrons and this guy wants electrons. Is that enough? Is that all I need to say?
And the mercury is aqueous.
Nope.
Is it not?
It's supposed to be. I mean, it is aqueous, you're right, but that's not why. This is lower on the activity series. So what does that mean if you're lower on the activity series?
More.
You want electrons more, right? The moment this magnesium has given its electrons to the mercury, they switch positions, right? The magnesium now has a +2 charge, and the mercury is a solid. So now I've got solid, or I've got this elemental mercury in a container with magnesium with a +2 charge. How come the mercury doesn't give the electrons right back to the magnesium? Because the mercury's lower on the list. So things lower on the list do not give their electrons up to things that are higher on the list, no matter what the situation is, spontaneously. All right, so I've got zinc ions, and I've got copper ions. Is there going to be any electrons transferred here? Nobody has any electrons. This is a no reaction. Nobody has anybody, there aren't any electrons to be transferred from one side to the other because they've already been given away in some other way. What about calcium metal and lead?
Does the previous one have anything to do with zinc being before copper?
It doesn't matter. If the zinc had its electrons, it would give the electrons to zinc, or to the copper, but it doesn't have anything to give. So what happens with this next one with the calcium and the lead?
Nothing.
They're
Nothing.
unstable.
everybody has their electrons. Nobody needs any electrons. There's no electron transfer. And the last one here is I've got silver, metal, and I've got sodium ions. So because the silver is a solid, does it have its electrons? Yes, so it could give them away. And because the sodium is not solid, it's aqueous, it's lost its electron. So can it accept electrons? Sure. So is the silver going to give it to it? No, why not?
Cause it's like really low on the list.
Because this is higher on list. So no. The metals that are more stable hold on to their electrons. So they will not give their electrons to a metal that's less stable than they are, less active than they are, unless they're being forced to. So the sodium will not be getting any electrons from the silver. So are we good with these last 4 questions? Do we see what needs to happen here? No?